Morning, ladies and gentlemen. My name is Leni Devera Asrar from Institute of Technology Budi Utomo. Today, I would like to present our paper. The title is KRL Lightning Protection System Method of Catenary Electricity Unit Stop Flow at the UPT Resort Region of Pasar Senen, Jakarta Pusat. Background. The modes of transportation are currently very diverse with the development of an area, and mass transportation is an absolute solution to the problem of congestion in urban areas in metropolitan Jakarta. The electric rail train moved through several stages, starting from the supply of a 20 kilovolt AC PLN distribution substation adjacent to the KI traction substation, and then being lowered through the KI traction substation step-down transformer to 1200 full DC. The AC power is then converted to DC using a silicon rectifier and finally generates a voltage of 1500 VDC, which supplies the KRL from the traction substation via overflow electricity or LAA with a catenary network transmission that runs across the top along the KRL route. LAA technical problems cause train travel disruption resulting in crossing and overcoming transverse trip cancellations or delays of 10 minutes or more. This is due to damage to the catenary network, so certain sections of the route finally cannot be passed by KL. The catenary network must then be safeguarded with protective facilities to secure other catenary network equipment from damage due to lightning strikes and induction. The study describes how to maximize the protection system on the catenary network in the area of the Technical Service Unit or UPT Resort LAA 1.7 Pasar Senen PT KAI Operation Area 1 Jakarta and is expected to be a reference for railway infrastructure employees at the LAA unit. The railway infrastructure consists of train track, train station, and train operating facilities, namely electrical telecommunication signal and overhead electricity, so trains can be operated properly. Upstream electricity, or what is often called LAA, is a system consisting of a traction substation and catenary network that functions to distribute electrical power from the source to the load. In this distribution, there are two processes of change. The voltage, namely the voltage will be increased using a step-up transformer to 70 kilovolt, 140 kilovolt, or 500 kilovolt. After it is transmitted and when it approaches the load, then the voltage is lower with a step-down transformer into a distribution system or 20 kilovolt. As can be seen in figure 1, the incoming voltage at DC substation is 20 kilovolt and is then converted to a voltage of 1500 VDC using a silicon rectifier and is used to supply KRL through the catenary network along with other supporting components. Protection facilities on the catenary network serve to protect other catenary network equipment from damage due to lightning strikes and induction. The protection facility consists of overhead ground wire OXGW, lightning arrestor and arching horn, and grounding equipment, as can be seen figure 2, 3, and 4. The catenary network along the railway line must be protected by a lightning protection system, including OXGW installed in the highest structure on the catenary network pole with a protection angle of 65 to 68 degrees, as shown in figure 5. The striking distance from the tip of the lightning tank to the object above the ground using the following formula: R equal 6.7 multiplied by E multiplied by 0.8. According to the distribution of peak lightning currents in the Jakarta area, the probability of 50% of the peak currents in the Jakarta area is 44 kiloampere. The striking distance from the tip of the lightning tank to the object above the ground was estimated using the following equation formula: R equals 6.7 multiplied by E multiplied by 0.8 meter. With the existing data of state, such as R equal 138.3. So the tracking distance in the Jakarta area is 138.3 meter. To calculate the angle of rotation according to the International Electrotechnical Commission standard, the equation was applied. By entering the existing data, it is obtained that the angle of protection or concrete pillars in the Jakarta area has an alpha angle of 67.45 degrees, and for the angle of protection for iron poles, an alpha angle of 65.95 degree is obtained. Visual result. Number 1, visual testing. In the result of inspection of the protection system installed on the catenary network, it shows that the components installed in the implement and root plots are still in good condition and summer one. These components are OXGW, cable clamp, grounding wire or down conductor, grounding root or grounding ring, arrestor, arching horn, and lightning rod at the traction substation. Number 2, grounding resistance test result. The result of testing grounding resistance measurements carried out on grounding installations of traction substation and catenary network, the GT, Rajawali, Pasar Senen, and Kramat average 1.08, 1.14, and 1.07 ohms, respectively, and it is good, meaning that the value still meets the standard according to the standard from WIL 2000 allows that the maximum resistance is 5 ohm. From grounding measurements carried out vary 6 poles with a distance of 50 meters per pole, and grounding protection only installed 2 poles. The average results are 2.07 ohm in pole 01 and 2.84 ohm in pole 06. This shows that the average value still meets the resistance standard, but the lack of lightning protection is dangerous and has an impact on equipment damage. Analysis result. The, the angle The angle of protection for concrete pillars in Jakarta area is 67.45 and the angle of protection for iron poles is 65.95. Based on the requirements, the OXGW must be able to protect the land and LAA with a protection angle of 65 to 68 degrees, and the data and calculation of the OXGW angle of protection installed on poles, either concrete or wool or iron types poles in the UPT LAA Pasar Senen area are appropriate. For the grounding installation distance on the pole and based on data, the calculations of the grounding installation distance on the Catenary network pole, the existing poles J1 equal 50 meter and P1 equal only 2 and are installed per 250 meters, providing a down conductor that is too far away and it can cause high voltage elevations because the ground inductance is getting bigger. The induced voltage from a lightning strike to the pull-on safety protection of 1,620 kilovolt is very dangerous. So the railway line is not safe, and therefore the solution is to install grounding along with a down conductor for each pole that exists. On each catenary network pole, all OXGW must then be connected to grounding with wire or iron. If each pole is grounded, the voltage occurs in the middle of the pole around 420 kilovolt. It can be seen that by grounding all poles, the voltage that occurred during lightning strikes is greatly reduced. So grounding all poles is highly recommended. Conclusion. Based on the result of the analysis above, it can be concluded that the optimum protection angle distance of the overhead ground wire is 67.45 for the concrete type pole, while the iron type pole is 67.95, and the two corners of protection still meet the protection angle protection requirement of 65 to 68 degrees. The grounding distance of catenary network poles on existing poles is installed every 5 poles with a distance of 250 meters, and this may result is a very high lightning strike induced voltage and very dangerous for human and surrounding equipment. It is suggested that it is necessary to install grounding on each pole with a distance of 50 meters to secure equipment and people along the railway line due to down conductors on iron poles or concrete poles. Recommendation for replacement of single and double silk types on station emplacement, while in traffic using the ST90 type is more economical, and for grounding rods made of copper, since the price is relatively expensive. and the material is prone to theft. It is therefore recommended to use iron. I think that's all of my presentation. Thank you for your attention.